So B just stands for base hydrolysis. And it's the same thing. If we have base in water, it will hydrolyze water to form hydroxide. If we have acid in water, it will hydrolyze water to form hydronium. And so this would be what's called a monobasic base. Monobasic. We could have, excuse me, dibasic bases and tribasic bases, like an A2 minus. The charge need not be negative. I mean, it could be neutral as well. If we have an A2 minus, that would be a dibasic base. And so a dibasic base could undergo two successive hydrolysis, that is KB1 and KB2. We'll look at this later. If we have a tribasic base, A3 minus, we'll have a KB1, a KB2, and a KB3. And so let's take a look at a monobasic base here. An example would be a 0.100 molar ammonia. The first thing is, this is ammonia and water. So if we have ammonia, it's a base, and the strongest acid present would be water. So we'd have ammonia and water react, which forms ammonium and hydroxide. And so our Kb is going to equal the ammonium ion concentration times the hydroxide ion concentration divided by the ammonia concentration here. That's our Kb. All right, so if we're given 0.100 molar ammonia, we assume that none of it's hydrolyzed yet. Water is pure liquid, so that's something. And then we allow it to hydrolyze, minus X molar, plus X molar, plus X molar. And so at equilibrium, we're going to have 0.100 minus X, X molar, and X molar. Okay, and so this is going to go to X squared over 0.100 minus X here. All right, we look up the Kb value. The Kb value is in our book. It's 1.8 times 10 to the minus 5. And that's the same number as the Ka value for acetic acid, but they're unrelated. You know, it's just the two sig figs are the same. But beyond that, they're different. And then we can solve for X. And so automatically, we just try the simplifying assumption. Because it doesn't take much time. We don't know if it's going to work or not. And then solve for our X here. And so I get 1.8 times 10 to the negative 5 times 0.1 equals that. And we'll take the square root of that answer. That's going to equal 1.34 times 10 to the minus 3. And then we have to justify this by calculating the percent change. Percent change is the X, the change 1.34 times 10 to the minus 3. Sometimes what I do is I like to use 0.100 because we can see the percent change more easily that way. Because if we say that's 100 parts, what was the change? Change is 0.00134. And so out of 100, you know, we move the decimal over, it turns out it's a 1.34% change. 1.34% change is fine because that's less than our 5% max. All right, so this is a base in water, but we call this step 1 because there's another step. If we have water present, there's something else that's going to contribute hydroxide to that, and that something else would be water autoionization. And so let's go ahead and calculate these concentrations here. This is going to give us 100 minus 1.34 gives us 0.099834 would be 6. The ammonia, this is going to be 0.00134 ammonium. And then the hydroxide, 0.00134. Okay, we have another equilibrium happening here. And the other equilibrium that's happening here is Kw, so we're going to call that step 2. Because, you know, if we're interested in the pH, you know, for basic solution, typically, you know, we'd get the hydroxide. From the hydroxide, we can go to the POH, and from the POH, we can get the pH. But we aren't quite done yet because of step 2. Step 2, H2O liquid plus H2O liquid is linked together with this equilibrium from the hydroxide concentration. And so why don't you do step 2 for me for this? Okay.
Yeah, I know, right? For like the whole 15, 20 minutes. So.
Sometimes, yeah, because I like don't get pictures, so I'll just like watch it.
Can you even hear it?
Well, I used to, but if I was like, I would be able to.
It's hard.
Yeah, sometimes there's a gland. Are you kidding me? Like, but I mean, but you know, like when yeah, and also when you're at home and you can pause, like you can go back. It's like you don't understand something. It's not that big of a deal anymore. But no, because like whenever I'm like, because last week I didn't know like I was like maybe I should like do like because I want to do well. So like come to lecture every time I do this, I'm like why do I come to lecture? Like I should like all the regret. Like
Want to go over it?
So what did you get on the first line here? For KW?
Is it 0?
0?
Yeah.
And hydroxide?
0.013.
Okay. And then this? Plus X. So the equilibrium, we're going to have X. 0, 1, 2, 4 plus X. Did somebody get X? All right, so I got 7.45 times 10 to the minus 12, which is fine. This is 10 to the minus 3, so the change is 10 to the minus 12. The initial is 10 to the minus 3 decimal places, times 10 squared, which gives us 10 to the minus 9, 10 to the minus 7. 10 to the minus 7% changes, no problem. So 7.45 times 10 to the minus 12 molar. And then the hydroxide is 0.00134 plus. Okay, I need 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 7, 4, 5. Okay, we can just do this calculation. Let's double 0, 1, 3, 4, 3, 6 zeros. 1, 2, 3, 4, 5, 6, 7, 4, 5. Did step 2 generate much additional hydroxide? No, there are two reasons we didn't expect much additional hydroxide. The first reason is the magnitude of K. You know, K is very small, 10 to the minus 14, so it's all reactant, right? And so we don't expect to generate much more. In addition to that, we have a whole bunch of hydroxide there present. if there was no hydroxide here present, what is the maximum amount I would have gotten? So if I started with 0 and 0, 0 and 0, I would have ended up with 10 to the minus 7 molar and 10 to the minus 7 molar. What we call that is, you know, I use the analogy, you know, would be the population of hydronium and hydroxide in an open field with no predators. In an open field with no predators, we get 10 to the minus 7, 10 to the minus 7, right? But now we have lots of hydroxide. If we have lots of hydroxide, as the hydronium increases, it's going to be attacked by the hydroxide. And that's going to keep the population way down. In fact, rather than generating 10 to the minus 7 molar, we generated 10 to the minus 12 molar, 5 orders of magnitude less, right, than what we would have expected. And so actually, I need to double check this because in case I made a mistake in the calculation. So let's check the K value here. 7.45 times 10 to the minus 12 times 0.00134 gives us, yeah. When I check the K, it comes out to 0.998 times 10 to the minus 14. So that checks out. That would round to 1.0 times 10 to the minus 14. And so we have another name for this. You know, it's not predator-prey, not open plains or whatever. The name for this, the official name, is the common ion effect. The common ion effect is this. When you have the ion here to begin with, we aren't going to expect as much forward reaction to take place. Let's go to the common ion effect. Well, anyway, we have to check. Now, this checks out here, but did step 2 perturb step 1? And so, you know, the ion here, this one, this is no longer 0.00134. That's what we got after step 1. Now we bumped it up. Now it's 0.00134 plus this little bit. This little bit, you think, is that going to upset our calculation over here? So if we plug in the new hydroxide ion concentration here, will this K still check out if I double check the K? Yeah, it's still going to check out. It's still going to be the same number. And in fact, we call this a negligible addition of hydroxide. And therefore, it's not going to perturb step 1, and in that way, we can solve this stepwise. All right, a strategy to this. If I was only interested in pH, I would have stopped at step 1. I wouldn't have done step 2. If I was only interested in pH, because look at, I would have gotten this much hydroxide, and now I added this much more. Is that really going to change the pH to the number of sig figs I'm allowed? No. And so if I was only interested in pH, I would do step 1. Now, your book will typically say step 1, and you can ignore the other steps, but that's not always the case. And so people want some kind of cutoff, some kind of rule. So for example, when do you have to worry about step 2, or do you ever have to worry about step 2 if you're only interested in the pH? Well, the answer to that is take a look at sulfuric acid. If you go back and look at sulfuric acid, step 2 significantly added hydronium to that. Whereas here, step 2 doesn't significantly add any hydroxide to this. This is a base solution, the other was acid solution. So we're talking about hydronium versus hydroxide. Well, looking at this, we wouldn't expect step 2 because 1, the common ion effect, and 2, the small value of K. Now go back to sulfuric acid and take a look at that problem. If we go back to sulfuric acid, we had the common ion effect, yes. But the K value was big. What was it? The K value for sulfuric acid. We called it Ka2.
Zero
0.011. Does that sound all that big to you? It doesn't sound big to you, but it is big. It is big because take a look where hydrogen sulfate lies on the acid chart. Hydrogen sulfate is in the boundary region between weak acid and strong acid. And so it's one of the stronger weak acids. Do you see that? And so hydrogen sulfate has a A of 0.011, or if you look at our chart, this chart has older data, it's 0.012. And so if you see a K value like that, then you got to reckon that there's going to be a significant contribution. But if you see a K value like this, I mean 10 to the minus 14, then there's not much of an additional contribution there. All right, these are little things that you'll see. The book tries to come up with some simplifications, but those simplifications can sometimes lead to a trap. And the trap is you get into the habit of ignoring step 2 if you're just doing pH, and then all of a sudden you have one that requires you to account for. So what we'll do is there are 2 types of calculations you do in chapter 16. One is where you're just interested in the pH. And if you're just interested in the pH, you're always looking for a shortcut, like for example, skipping step 2, step 3, whatever, if it's possible. And the other type of calculation is where we do the inventory. When you do the inventory, you have to do the complete calculation. So let's look at the inventory we just generated. So if I have a beaker that's labeled 0.100 molar ammonia, NH3, what are the species and the concentrations I expect to find? Well, one species is ammonia itself. What was the concentration of ammonia? Ammonia was about 1.3% reactive, wasn't it? And so what we're going to be left with is 0.0986. Is that it? 6 molar. All right, so not at the full 0.100 because it's a weak base. Weak bases are partially ionized. Well, what is the percent ionization? How much did we lose? Well, out of 100, we only lost 1.24, 1.34, right, percent. All right, the next species here is going to be hydroxide. Hydroxide is going to be present at 0.00134 ... molar. And then ammonium. The hydroxide is going to be a little bit more than this. The ammonium is going to be at 0.00134 molar. And then the hydronium here is going to be at, what was the hydronium concentration?
7.45 times 10 to the negative 7.
Okay, thanks. Now there are 2 ways to get the pH. If we've gotten the hydronium, then we could just take the negative log of that. The most common way for base solutions is we get the pOH. Now pOH is just the negative log of the hydroxide ion concentrations, so it's 0.00134 ... And so that gives us a pOH of what? Okay. So take the negative log of 0.00134. I'm not going to add all those other digits to it. And so the pOH comes out to 2.87. I'm allowed 2 sig figs, so I'll carry 1 extra, 872. And then to figure out the pH is just 14.00 minus the pOH. So do that. We come out to 11.127 the pH. If I took the negative log of this directly, I should have gotten the same answer here. I just take the negative log of the hydronium concentration. Okay, any questions on this? No?
The hydronium concentration is 10 to the negative 12.
Oh, 10 to the negative 12. So. Okay, next solution we're going to look at is a tribasic base. So this example is going to be 0.100 molar sodium phosphate. All right, I'm going to do a preliminary step here. I'll call it step I. Step I is this. It's sodium phosphate. Well, what happens when you dissolve it in water? And so, well, it dissolves because sodium salts are soluble. And so the question that comes up next is, what are the species that are present when it dissolves? And so when it dissolves, we expect soluble salts like this to be strong electrolytes. Strong electrolytes ionize completely. A lot of people do this step in their head, but we'll just do it. You know, K is going to be very large because anything that goes to completion should be very large. And so initial would be 0.100 molar. So we'll say none of it has ionized yet. And the change is going to be complete. And so we're going to lose all this, 0 molar. And that means we're going to form 0.300 molar sodium ions and 0.100 molar phosphate ions. So you could do this in your head as well. You don't have to do it in an ice table like this, right? And so really our starting point is the phosphate. So far we've generated 0.300 molar sodium ions. That's going to stop here. Those aren't going to undergo any further reaction, but the phosphate will, because phosphate is a pretty decent base. Take a look at where phosphate lies on the acid-base chart. If you look at where phosphate is, it's on the lower right-hand side. Do you see it? It's right at the border between weak base and strong base. So phosphate is one of the stronger weak bases. And we'll go on to step 1. Step 1, we expect, well, the phosphate is a pretty decent base, so that should hydrolyze water pretty well to form monohydrogen phosphate and hydroxide. And then we look for the Kb value for this. This is base hydrolysis, but we can't find the Kb because looking at that chart, they're all Ka values, right? And so what we have to do is we have to use the conjugate relationship. And so let's take a look at the conjugate relationship here. Kb equals question mark. And so the conjugate relationship is like this. Ka times Kb is equal to Kw, as long as Ka and Kb are conjugates of each other. And the way this works is, Ka is going to have hydronium times A minus, this equation we had earlier, divided by the HA concentration. Kb is going to be the HA concentration times the hydroxide ion concentration divided by the A minus concentration. And so this is my Ka and this is my Kb generic form. HA's cancel. A minus is cancel. That leaves us hydronium times hydroxide. Well, hydronium times hydroxide is just Kw. And so the only way HA will cancel and A minus will cancel is if they're conjugates of one another. And so what that means is this. This is Kb1 for phosphate is going to equal Kw over the Ka for the, what's the conjugate acid of phosphate? Conjugate acid of phosphate is monohydrogen phosphate. So Kw is 1.0 times 10 to the negative 14. Ka for monohydrogen phosphate is 4.2 times 10 to the minus 13. 4.2 times 10 to the minus 13. This is different than on that chart. That's why I'm not using that chart. I just want to use the book's value. The chart up there has it at 2.2 times 10 to the minus 13. Okay. And so what does this give us? Well, let's go ahead and punch this out. That's 1 times 10 to the negative 14 divided by 4.2 times 10 to the negative 13, which gives me 0.0238. 0.0238. Now, if you see a value of 0.0238, what do you think of that? Is that small? I mean, 0.0238 seems like a pretty small number, doesn't it? But this is a K, so if you see a K value of 0.0238, you would think small and insignificant or kind of big. This is kind of big, because if you remember sulfuric hydrogen sulfate, hydrogen sulfate was 0.011, and it was kind of big. And so this is kind of big, meaning that this is borderline strong. Although, going from 0.0238 to very large seems like a huge jump. But this is pretty good size KB. The bigger the KB, the stronger the base. Okay, so why don't you fill out the ice table now? Let's see what we have. So we know the KB value, and we try to do things stepwise. This is a tribasic base, so there's going to be KB1, KB2, and a KB3. KB1 for phosphates is just equal to the KB for phosphate. And why don't you fill this out and tell me what it comes out to at the end of step 1. All right, let's fill in the table here. And what did you guys get? First line. 100. Water? Nothing. HPO4, 2 minus? 0 and 0. All right, change. Let's go straight to the equilibrium. What is this?
0.1 minus x.
Okay, 0.100 minus x. Let's try to keep track of the sig figs, and this is going to be x and x. And did you calculate it? Let me ask you, did the simplifying assumption work or fail?
Fail.
It failed. What was the percent change? 48%. 48% is too high. So you use the quadratic equation? Okay, and what did you get for x?
0.038315.
0.0383? All right. We'll just go one extra digit here. And so what we see here is, if we start off with 0.100, we lose 0.0383. So what this is 38.3% reaction, because I like to start off with 100. And so we can see a 38.3% reaction, that's significant, So this is getting borderline, 38.3% hydrolyzed. This is starting to get borderline strong or stronger base. And so this is going to give us 0.0617. And so 61.7% remains unionized, 38.3% was ionized. The HPO4 2 minus was 0.0383 molar, and the hydroxide 0.0383 molar. Did you double check this? And it checked out okay?
Yeah.
Good. Except we aren't done yet because of this. This is a tribasic base. And so that means this HPO4 2 minus is also a base, and that can generate additional hydroxide. And so we're going to go on to step 2 now. Step 2 would be KV2. And KV2 is going to be the HPO4 2 minus that we just generated, hydrolyzed in water, H2O liquid, to form, okay, when that hydrolyzes, we're going to form dihydrogen phosphate and hydroxide. And so we're going to generate more hydroxide. This is called KV2 for phosphate. KV2 for phosphate is equal to KB for monohydrogen phosphate. Kb for monohydrogen phosphate is equal to Kw over the Ka for what acid? What's the conjugate acid of monohydrogen phosphate? Dihydrogen phosphate. And so dihydrogen phosphate would be it. This should be, sorry, 2 minus. You all right, Don? Okay, so we look up, we have the Ka value for dihydrogen phosphate. So we got 1.0 times 10 to the minus 14 divided by the Ka value for this. The Ka for dihydrogen phosphate is 6.3 times 10 to the minus 8. Go over here, 6.3 times 10 to the minus 8. And then I do the calculation, see what it comes out to. So 1 times 10 to the negative 14 divided by 6.3 times 10 to the negative 8. Switch that over. So this comes out to 1.58 times 10 to the negative 367 times 10 to the negative 7. Is that what you guys get? Yeah?
Where did you get the 6.3?
Oh, that's given. This is from a book. Our chart says that the Ka is 6.23, but I just want to use Petrucci's numbers. And so this is off the table. The tables, you know, when you look at the tables, some Kb values are given, like ammonia is given. But most of the Kb values aren't given because they just use the conjugate relationship to figure out all the Kb values. And so we only see one table typically, and that's a Ka table. Okay. There's no reason to actually print out a second Kb table. But you look at this, and so let's go ahead and plug in. What are the values we plug in for the first line? Why don't you guys do that? Just the first line there. All right, for the monohydrogen phosphate, what did you put here? 0.038. For the water? Nothing. Dihydrogen phosphate? Zero. Hydroxide? Zero. Zero, yeah, 0.0383. Why? Because we have generated hydroxide here, so there's already hydroxide present. And so this one goes down to step 2, and this one goes down to step 2. Both of these go down to step 2. And so we're starting with this. The change here is going to be to the right, so at equilibrium we're going to have 0.0383 minus x. I'm going to skip a step here. because I want to save a little bit of time. And this is 0.0383 plus x. And so when we think about this plus x molar here, if I was interested in pH, would I do this step or would I skip this step? I mean, just stop over at step 1. And if I was interested in just the pH of this solution, the question is, do you think step 2 is going to contribute much more hydroxide, a significant amount that we should do it? No. In fact, if I was just interested in pH, I would have stopped here, because I wouldn't expect much additional hydroxide. One, the K value is like 10 to the minus 7, not like 0.01. If the K value were 0.01, I would do it. You know, 0.01, 0.02, something like that, I'd do it. 10 to the minus 2. But this is 5 orders of magnitude smaller, at 10 to the minus 7, I wouldn't do it. And 2, we have the common ion effect. I mean, if you already have a lot of product here, we don't need much to fulfill the equilibrium constant expression. So if I was interested in pH, I would stop here, calculate my pH, and be done. You know, I'd have to get my POH and then figure out the pH from that. If I'm interested in the inventory, then I have to do the whole thing. Well, I'm interested in both, so I'm going to do the whole thing. In other words, let's go ahead and do this. This is going to equal. What does this equal? This is going to equal the dihydrogen phosphate concentration times the hydroxide ion concentration divided by the monohydrogen phosphate concentration. And so it equals 0.0383 plus x over 0.0383 minus x times x up here. Then I use that simplifying assumption. If I use the simplifying assumption, then this goes to 0.0383 times x, and the bottom goes to 0.0383. Well, the 383's cancel, and I get this. I get x is equal to KB2. Your book does this. Your book says that is x equal to KB2? Well, it is in this case. Is it always the case? It's not always the case, but your book comes up with this simple pattern that they observe, and it can fail. But in this case, it would work because KB2 is 1.58 times 10 to the negative 7. Was the simplifying assumption valid? Yeah, because this is 10 to the minus 2, so the percent change is, when this order is of magnitude, the change was 10 to the minus 7. Oh, no. Change is 10 to the minus 7 over the original 10 to the minus 2 times 10 to the minus positive 2%, which is going to give us 10 to the minus 7%. The percent change is fine. So x is equal to KB2. Just because of the funny way things canceled out. Well, anyway, let's go back over here. This is going to be 0.0383 minus x. X is going to be 6 zeros, so 1, 2, 3, 4, 5, 6, and then a 158. 0, 0, 0, 0. This is going to give me 1, 4, 8, 9, 9, 2, 8, 3, 0, 0. Okay, so I went from 383 to 3829. Was that much of a change? And I barely lost any. And then over here, I formed a little bit of dihydrogen phosphate, 1.58 times 10 to the minus 7. And then over here, I gained a little bit, so 0.0383 plus, I need 6 zeros. 3, 6 is too many. 158. So I need to extend this. So I'm going to get 0.038, so 300158. Hey, did I gain much over here? I went from 383 to 383 plus this a little bit at the end. No, it's not much. That's what we call negligible addition. Well, let's double check this, make sure it checks out. And so we'll check the K value here. Checking the K value, I've got 1.58 times 10 to the negative 7 times 0.00383 0.00158 divided by 0.038299841, and I get my K is 1.580 times 10 to the minus 8. 10 minus 8, I screwed up. 1.580 times 10 minus 8. So let me see where I screwed up. 1.58 times 10 to the minus 7 times 0.0383 divided by 0.03829. Oh, I screwed up on my calculator. It's okay. All right, the K checks out, but we also have to do something else. When we're doing stepwise, we have to make sure that this step does not perturb the previous step. So did it perturb it or did it not perturb it? Because the previous step, it checked out. Did we double check this calculation? Did I? I better do it. I got to make sure. We want to check the K value. We're going to use these concentrations here. 0.0383 squared divided by 0.0617. And that comes out to K is equal to 0.02377. We had 0.02388, so that's good. So that checks out. But now, you know what? Step 2 changed these concentrations. If step 2 changes these concentrations, will it still check out? And so what step 2 did was it reduced the HPO42 minus and increased the OH minus a little bit. And so will it still check out? In other words, did step 2 perturb step 1? The answer is no, because these are just negligible. I mean, this would round up to 383, this is already 383. And so there's a negligible change in step 2. Therefore, step 2 does not perturb step 1, and we're still okay doing this stepwise. Well, let's continue on to step 3. Well, we have to see, do we do step 3 or do we do KW? Step 3 would be KB3. And so when we generate this, oh, wait a minute. There's something, there's something about this one, step 2. Monohydrogen phosphate is what we call amphoteric. Amphoteric species can hydrolyze water either as an acid or base. And so let me do an aside here. I'm going to call it step 2B. Because monohydrogen phosphate is amphoteric, which means it can collide with water to form hydronium, like this. It collides with water to form hydronium and form phosphate plus hydronium. Or it could collide with water to form hydroxide. If it collides with water to form hydroxide, we form H2PO4 minus plus OH minus. Both these collisions can occur. So for example, this is Ka, this is Kb. This is Ka for monohydrogen phosphate. This is Kb for monohydrogen phosphate. And so if we have a Ka collision, well, the Ka value was, I had that up there earlier. The Ka is 4.2 times 10 to the minus 13. And then the Kb value we just calculated. The Kb value for this was 1.58 times 10 to the minus 12. Is that it? No, sorry. Was it Kb for monohydrogen phosphate? Sorry, Kb for monohydrogen phosphate is 1.58 times 10 to the minus 7. Hey, so it's much better. The Kb looks much more favorable, 10 to the minus 7 versus 10 to the minus 13. But can you tell monohydrogen phosphate? That is, water water can collide both ways, right? It can generate hydronium and hydroxide. Can you tell water not to generate the hydroxide, only to generate the hydronium? Is that possible, to turn off a set of collisions? No, the same thing here. Can you turn off, you know, I don't want the Ka collisions because I don't want to deal with Ka, I just want to deal with Kb. And so what I want to do is I want to turn off this collision here. That is, when the monohydrogen phosphate and the water collide, I only want the proton to transfer from the water to here. But I never want the proton to transfer from here to the water. Is it possible to say, okay, we can transfer protons this way, but we can't transfer them the other way? Is that possible to do? No, it's not possible. The collision is going to happen. And so what that means is, yes, I have Kb. I just did the Kb. This is a Kb collision for monohydrogen phosphate. But I also have Ka collisions. So don't I have to worry about the Ka collision as well? And so if I have to worry about the Ka collision, well, I better take that into consideration because that's a Kb collision. This would be the Ka collision. That is, monohydrogen phosphate and water hydrolyzed to form hydronium plus phosphate. Right? And then I know that the Ka for this is 4.2 times 10 to the minus 13. And so I'm going to call this step 2b. And so what I'm going to do is I'm going to take this concentration, 0.03829, 0.03829, molar. And then the hydronium should be 0. And the phosphate, what was the phosphate from earlier? It was 0.06, step 1, step 1. 1.7 molar. All right, so this comes from step 2. This comes from step 1. And so then at equilibrium, you know, I'm going to have, this has got to go to the right, so it's going to be 0.038. I'm going to not write everything, minus x molar, and then 0.0617 plus x molar. And so I have to account because monohydrogen phosphate can collide with water to form hydroxide, or monohydrogen phosphate can collide with water to form hydronium. Since I can't tell monohydrogen phosphate what to do, it's just going to do it. I have to account for this because this is another equilibrium in my mixture, correct? But there's something special about this. Take a look at this and compare this to step 1. Compare to step 1. And so since we're running out of time, I'll just tell you in the comparison. This describes the equilibrium between monohydrogen phosphate and phosphate. Oops, go here. And phosphate. Step 1 describes the equilibrium between phosphate and monohydrogen phosphate. And so they both describe the same equilibrium. The difference is this. This one in terms of hydronium, in terms of H3O+. This one describes it in terms of hydroxide. Well, hydronium and hydroxide are connected by a seesaw relationship called Kw. And so it turns out that this is redundant. Step 2b is not necessary. This is a repeat of step 1 if we do it this. And so this brings us to a simple rule. You know, this is not necessary. The simple rule is this. If you have a base solution, so bases, you only consider hydroxide generating steps, hydroxide generators, i.e. Kb, the Kb's, and Kw. You never look at a Ka And so do not consider KAs. Because if you consider KA, then you're going to be doing a repeat of something like this. Do not do KAs. For acids, you only look for the hydronium ion generators for contributors. Hydronium contributors, and we don't do KBs. Don't do KBs. And so here we're about to insert a Ka step in a base solution. We don't do that. We don't do that because that equilibrium is already accounted for. And it goes for any of the other Kas that you can think of in this mixture. And so I didn't quite finish. I'm going to spend the first part of tomorrow's lab just to finish this problem. Almost done.